The zeroth law of thermodynamics is just saying if two separate systems, or two systems are found to be in thermal equilibrium with a third. So, like, I measure one thing, and then I measure another thing. They're both equal in thermal equilibrium with that third object. Then the two original systems are in thermal equilibrium. It's like the transitive property, kind of. You can think of it like that. A simple way of writing it is, if A is the same temperature as C and B is the same temperature as C, then A and B are the same temperature. So, there we go. The first law of and that's just dealing with the law of conservation of energy. Thermal energy can change form and location, but it cannot be created or destroyed. List 2 ways thermal energy can be increased in a system. Just from the PowerPoint, it says that the thermal energy can be increased by adding thermal energy, so adding heat, you heat it up, or by performing work, so like using some kind of friction. So that's pretty simple. Let's move on, huh? All right. The second law of thermodynamics is just saying that thermal energy flows from hot to cold. So, just from hot to cold. That's pretty simple. If we are to define entropy, it's the measure of how evenly distributed heat is within a system. So a low entropy would mean everything's nice and ordered. High entropy is like it's very chaotic and everything's in disordered. Convection, defining convection, remember that was a method of heat transfer or thermal energy transfer that's through a liquid. So it could be a fluid, which could be considered a liquid or gas. So energy transfers through a fluid. For me, I think of a convection oven or like a space heater. It heats up the air, and the air rises when it gets warm, and then the cool air falls to the heater, and then it just cycles around. List 2 examples. I just did 2 examples of convection. A convection oven, or like a space heater in a room. Conduction is the transfer of thermal energy through touching, from molecule to molecule. So there's that, and it's pretty good. We're on 15. Okay, keep going. List 2 examples of conduction. While the example from the notes was there was soup heating up a spoon, because, well, it's kind of like a fluid. No, it was like you're touching something hot. So maybe this will be better. There's like a hot pan on the stove, and you put like an egg in the stove. The thermal energy is being transferred from the pan to the egg by conduction because they're touching. Another example of thermal energy is just maybe like you when you hold a cup of coffee, you hold your hands around it to warm up your hands. Warming your hands on a hot cup of coffee. That's by conduction because you're touching the warm cup. The heat is actually being transferred from the coffee to the cup by conduction, and then from the cup to your hands also by conduction. Conduction equations. There you go. This is the heat transfer stuff. Let's define the variables. I'm just going to write them down. I'm literally copying them from the PowerPoint. Q is the energy transfer in joules, so it's the energy transfer between objects. M is the mass of a material, whatever material you're looking at. And then C is the specific heat capacity of a material. Remember, the specific heat is a characteristic of a material, and it's the amount of energy, the amount of joules to raise the temperature of the material 1 degree Celsius or whatever. It's defined based on whatever material you have. Let me get the rest. P is the power, which is the rate of energy transfer in watts. Remember, 1 watt is 1 joule per second. Then we have the change in time. delta lowercase t is change in time. T sub f minus T sub 0. K is the thermal conductivity. It's a characteristic of the material. If I remember right, it's like a measure of how well it transfers heat. A is the area of thermal conductivity, so it's just the area that's having the heat transfer. L is the thickness of the material, and delta capital T is the difference in temperature, change in temperature. And that's, remember, just Tf minus T sub 0. You can use that. Okay, so this is the real reason. This is the real reason why I wanted to do this video. A 1 kilogram piece of aluminum metal at 90 degrees Celsius is placed in 4 liters, which is 4 kilograms, of water at 25 degrees Celsius. Determine the final temperature, T sub F. All right, list all known values. That's, I forgot, I don't know what number that is. So here's what I know. The mass of aluminum is 1 kilogram. The initial temperature, T sub 0 for aluminum, is 90. The mass of the water is 4 kilograms, and the initial temperature of the water is 25 degrees Celsius. I also know, these are things that I also know, I know that the final temperatures will be equal. So that's something. So TF, I'm just going to use TF, I'm not going to use the subscript W or aluminum, AL. I'm also going to tell you and write down the specific heat capacities. So C for water, that's 4184 joules per kilogram degrees Celsius. And C, the specific heat capacity of aluminum, is, I think, 900 joules per kilogram degrees Celsius, kg degrees Celsius. Well, yeah. If I find out more later, then I'll add it. Let's go on to number 19. The unknown values. Well, I don't know. No, I know the mass of aluminum. Okay. I guess I don't know the. Whoops. I don't know the final temperature. So T sub F. I can just call it T sub F. What else don't I know? I think that might be it. Well, let's see. Select equations. I'm going to use. Do I know the energy transfer? I do not know the energy transfer. That's something. So I don't know Q, which is the energy transfer between the two. The equations. Well, first I know that Q for aluminum is going to be the same as Q for water. The energy transfer between these two objects is going to be the same. It's just one's going to be negative, one's going to be positive. The aluminum is hotter than the water. So because of the second law of thermodynamics, the energy transfers from hot to cold. So the aluminum will be losing energy. The water will be gaining energy. So we have this. So yeah, there we go. That's one equation, and then the other equation is, I'm going to say, is the MCAT equation. C delta T. And what I'm going to do, I'm going to use this fact. They are going to be the same, so I'm going to think about, well, for aluminum, and I'm also going to think about the equation for water. And it's the same, but we'll put in different values. So if I just write down for aluminum, I have, I guess, the mass of aluminum, which was 1 kilogram, times the specific heat, which was 900 joules per kilogram degrees Celsius, and the temperature difference. I'm going to write that as T sub F. Remember, that's both for water and aluminum, minus T sub 0 for aluminum. And that, by this equation, has to equal the MCAT equation for water, which is 4 kilograms, because we had 4 kilograms of water, times the specific heat, 4184 joules per kilogram degrees Celsius, And then, what do we have? Times T sub F minus T sub 0 for water. And I know that. Oh, maybe I should write that in there. Yeah, I'm going to write that in there. So I'll erase this. For aluminum, it was, I think, 90 degrees Celsius. For water, it was 25 degrees Celsius. So there we go. I will multiply this stuff together and solve. 1 times 900 is 900. I'm going to take this and distribute it. And then 4 times 4,000, blah, blah, blah. I'm going to take that and distribute that as well. So I'll rewrite that down below. Notice how my units cancel out. The kilograms will cancel. The degrees Celsius will cancel on each of those. So I'm just left with joules, which is good because these are equations for energy transfer, which is in joules. So I distributed those two, and I'll get the letters to the left and the numbers to the right. So I'll add or subtract those over. I'll do this first. 81,000 joules plus 81,000 joules. And then I'll do, well, that goes away. I'll rewrite the next part. So then we have that, and I'm going to subtract 16,736 over joules times TF. These are like terms, so I'll have a negative energy over here, but I have a negative energy over here, so that makes sense. And then we'll divide, and we'll just get degrees Celsius. Right? Yeah. Okay. So let's write that. Oh, wait, you know what? I did this part wrong, and I don't have time to correct it. But this actually, I was supposed to make this side negative, right? I didn't pay attention to that part. Well, I'll go over this part in class. Sorry. Goodbye.